Hello, everyone, and welcome back. We did it, right? So in this class, we are going to talk about one of the most important theorems in all of calculus. It's so important, we call it the Fundamental Theorem of Calculus. So the first question you might have is, what is so fundamental about this theorem? Well, what the theorem that I'm going to present to you over the course of this class and prove, what it really does is it intertwines and shows us a connection between two of the most important concepts in all of calculus, the derivative and the integral. And you probably have seen this, especially if you've taken an introductory calculus class before, but you can always sort of think of integrals as undoing derivatives, and maybe a harder direction to look in is that derivatives undo integrals. That is what the fundamental theorem of calculus really does. Now, I want to just pick apart something that I just mentioned, and I want to interrogate it for a second. A lot of people seem to think that calculus is the study of derivatives and integrals. Sometimes people think it's just the study of functions. But I want to pick at that. And I want to remind you that calculus is not the study of derivatives and integrals. These things are consequences of our definition of limits. Calculus is the study of limits. Go all the way back through this class. What is the one constant? Limits. It has been what we use to define the Riemann integral. It's what we use to define continuity, to understand functions. It's what we use to define the derivative. And it's what we're going to use again today in order to prove the fundamental theorem of calculus. So if you get nothing else out of this class, but take one thing with you, and that is calculus is the study of limits. Now, let's go ahead and let's start talking about the fundamental theorem of calculus. Now, what we'll do is we're going to break the fundamental theorem of calculus into two parts. So we have the fundamental theorem of calculus version 1 and version 2. Let's kick it right off. Let's talk about version 1. So this is the fundamental theorem of calculus version 1, so V1. Okay, this is probably the one you're more familiar with. This is for definite integral problems. So let's say, suppose we have a Riemann integrable function on a closed interval a to b, and suppose that there exists some function f such that when you take the derivative of f, this thing is equal to little f everywhere on the interval. Okay, so we typically refer to capital F as the antiderivative. Well, then we know, or you probably know from an introductory calculus class, that if you are going to integrate f of x, little f of x over a closed interval, this is just the same as evaluating the antiderivatives at the endpoints and subtracting them from each other. Now, the cool thing about this is how we approach the proof. If you remember in the previous lecture, we proved the mean value theorem. And I said it's an extremely critical theorem, even though it looks very benign. It doesn't look like it's doing a whole lot of work, but the mean value theorem lurks in the background of a number of our important results in calculus. And this is going to be a glimpse into where that comes in. So let's take a look at this. We're going to prove that the integral of f of x over the interval is equal to this capital F of b minus capital F of a. So we know by hypothesis, for all epsilon greater than 0, there exists a delta greater than 0, such that if we take our partition and our mesh, so you might have to remind yourself a little bit about integrals. It's been a while since we've spoken about them. But this implies that the Riemann sum of little f for any choice of evaluation points minus the actual value of the limit. Remember, this is just the value of the integral. Remember, this is just a shorthand for a limit. This thing is less than epsilon. Okay, so then let's let let's let epsilon be greater than 0 and P be a partition such that the partition is small enough with respect to the delta value that comes from that epsilon. Okay, now that relationship that the Riemann sum is within epsilon of the actual value of the integral, that works for every single choice of your evaluation points, xi bar. So here's what we're going to do. We're going to choose those evaluation points. So by the mean value theorem, MVT, in each subinterval, so in each subinterval, xi minus 1 to xi, we can pick our evaluation point, xi bar, such that capital F prime of xi bar, that's little f of x. Remember, that's by assumption. This is our f, capital F is the antiderivative, f prime is the little f function. So this thing right here, maybe I can just draw underneath it just so you can really see. This is f of xi bar delta xi. And of course, we recognize these as coming up in the Riemann sum. Well, from the mean value theorem, this is the same as evaluating capital F at the endpoints and subtracting them, right? So the evaluation point exists in that interval by the mean value theorem. But if we do this for every interval, this tells us that my Riemann sum for those, or for that choice of evaluation points, well, let's put all this in. This becomes I equal to 1 to n. Let's write it out first. As I just said, this little f term, you can equivalently write that as f prime of xi bar times delta xi, which from the mean value theorem and our choice of evaluation points, this tells us that this is capital F of xi minus capital F of xi minus 1, which now we have a telescoping sum. We're adding and subtracting endpoints. We've done this tons of times in this class now. This leaves us with the right endpoint minus the left endpoint. So what this says is the Riemann sum for this specific choice of evaluation points is equal to exactly capital F of B minus capital F of A. But remember, this implies, since my little function f is Riemann integrable, this implies that this thing right here, this value, is within epsilon of the actual value of the integral. This is less than epsilon. And this is true for every epsilon greater than 0. It doesn't matter what the value of epsilon is. I can always say that this is true just by following the above manipulations. But if this is going to be true for every positive number, I can just keep making this thing smaller. And the only way that's ever going to work is if the thing inside of the absolute value is equal. So this tells me that the only way this is possible is if the value of this integral is equal to exactly what we said it would be in the theorem. That's pretty cool, right? I think that that's a really interesting result, and it's a nice application of the mean value theorem. I mean, on the surface, when you first see the fundamental theorem of calculus, this version of it, especially if it's not given with a proof, it kind of feels like a little bit of magic, right? It's hard to see exactly where that antiderivative pops out. Now, another piece of this is that this is what I called version 1 of the fundamental theorem of calculus. There is a second version of this that relates derivatives with respect to x to integrals. Before I can get there, I need to provide for you a different version of the mean value theorem. So this is called the mean value theorem for integrals. Now, if you remember from last lecture, The mean value theorem that I gave you was for derivatives, right? We just used it in the previous proof. There is a version of the mean value theorem that also works for integrals. And I'm going to give it to you. I'm not going to give it with a proof. I'm going to leave the proof as a nice little exercise. I will give you a hint. You can use the intermediate value theorem to prove this, but I want you to try and interrogate it yourself. Have a little bit of fun, right? It doesn't have to be me having all the fun of it. So let's say if f is a continuous function on a closed interval AB, then there exists some C in AB such that f of C is equal to 1 over b minus a times the integral of this function. Now, in my opinion, the mean value theorem for integrals is actually easier to understand than the mean value theorem for derivatives. And why is it that I say that? Well, you may be familiar with this on the right-hand side. This is the average value of f of x on the interval AB, right? We remember maybe this formula from intro calc. This is, you take the integral over the entire space and then divide it by the length of space. And so what this is really telling you is that there is some point in the domain that hits your average value, right? So we call this a mean value theorem for integrals, but it's a lot closer to sort of intermediate value theorem. And of course, that's why you're going to use the intermediate value theorem to prove this. So like I said, I'm not going to prove it. I'm going to use it in the next proof here. And I'm going to leave this as an exercise for you to have a little bit of fun with. See if you can get through it. If you have some trouble, try and contact me and we can talk it through. Okay, so let me give you the second version of the fundamental theorem of calculus. So FTC stands for Fundamental Theorem of Calculus. I know that there's a lot of abbreviations, but there's also just a lot of writing. So Fundamental Theorem of Calculus version 2. Let's suppose f is a continuous function on a closed interval. And let's define, so this case, we don't have an antiderivative. We are actually going to define an antiderivative. So let's define some capital F of x equal to an integral where the upper bound here depends on x. Sorry, this should be f of t because I'm already using x. So I have a dummy variable inside the integration. And what this says is, again, if you're thinking about integrals in terms of areas, this is saying the area from the beginning of the interval up to some point x. And so you can think of capital F as like an area function. Okay, this is for all x in AB. Great. Then f prime exists, so we've created a differentiable function, and its derivative is equal to, it's equal to f of x everywhere. It's equal to little f of x. So basically what we did with this is we created an antiderivative. This is what you use extensively for indefinite integrals. Now, you typically don't use it in this form, but if I say, find this right here, and you give me x cubed over 3 plus c, don't forget about the plus c. The plus c part is taken care of by this lower bound. Maybe I'll circle it so you can see it. This lower bound right here. So when we apply this in maybe an intro calc class, we don't actually put bounds on these integrals. And so we typically put this plus c on the end. Now, what this theorem is actually telling us is that you can get rid of the plus c part by just fixing your value at the beginning of the domain. Okay, so this allows us to define antiderivatives of functions using integrals, right? So let's take a look at these again. The first thing here is that this tells us that derivatives can be used to understand integrals. And version 2 tells us that integrals can be used to understand derivatives. This is the intertwining of the fundamental theorem of calculus when you put these two things together. And let's take a look at the proof. So we have f of x defined. We want to show that its derivative exists and that it's equal to little f of x. So let's look at the difference quotient. Remember, this is the thing that we take the limit as h goes to 0 to define the derivative. So the difference quotient, capital F of x plus h minus capital F of x divided by h, right? This is the thing we want h going to 0 in. Well, I'm going to take the 1 over h out front. And now, since capital F is defined in terms of these integrals, if you go back to some of the properties of integrals we're essentially have two different upper bounds. And so you could actually put this as x to x plus h of f of x dx, right? This is the area that's left over by going forward a little bit more, the x plus h, as opposed to just going forward to x. So you can do a little manipulation. You can find that out really nicely. And here's what I'm going to do. I'm going to use the mean value theorem for integrals here. So let's take a look at this. If I look back at the mean value theorem for integrals, my space here is x to x plus h. Of course, my function is continuous by definition. And the length of my interval is h, so that's the 1 over h being divided out here. And so the mean value theorem for integrals tells me that this thing is just equal to f of some, say, x bar with x bar between x and x plus h, right? It's in the middle of that little interval. Now, what you can see here now is that f of x bar, as h goes to 0, well, then this little interval that x bar has to live in gets smaller and smaller. You get crushed into x. And so, of course, this thing converges to f of x. But what does that show you? That shows you that the derivative of capital F is equal to little f. Right? Because this is taking the limit as h goes to 0. That's what my little arrow notations have done here. And so this proves everything that I wanted here. So that was a super easy application of the mean value theorem for integrals. And of course, I kind of hid the hard part in the background for you because I'm making you prove the mean value theorem for integrals. But I do think it's a valuable exercise. I do think that it's worth trying out. But that's it, right? Now we have the full fundamental theorem of calculus, version 1, version 2. We've got them both, and now we have a complete relationship between derivatives and integrals. Now we're going to finish off this lecture with another important theorem in mathematics or in calculus, and this is called the Intermediate Value Theorem for derivatives. So we've seen the Intermediate Value Theorem before. This is another version of the Intermediate Value Theorem, and this applies to derivatives of functions. So here's what I want to do. I want to start by writing down this theorem and showing you what it says. But in my opinion, this theorem is kind of hard to disambiguate, sort of what it is geometrically that it's telling you. And then, so once we write it down, then we'll sort of interrogate it a little bit. We'll try and understand what it's saying. So what this says is that if f prime of x exists for all x in some interval, then f prime has the intermediate value property. So intermediate value property. And you might have to remind yourself what the intermediate value property is, but don't worry, I'm just going to write it down for you right here, so you don't have to go back through your notes. So what this really means is that, namely, if A and B belong to this interval, and y lies between f of a and f of b, f prime, right? This is the intermediate value theorem for derivatives. I forgot the prime. Then there exists an x bar between a and b such that f prime of x bar is equal to y. Okay, so basically this shows you that if your derivative exists for all values, then it has the intermediate value property, right? It hits everything in between any 2 points that you can find in the range here. Now, what's the sort of geometric intuition here? Well, I thought about ways to help you understand this, and I couldn't find a better one than a math stack exchange answer. So how about I just show you exactly what it says there? Let's see what it is that I want to show. So let's see, just a second. Pardon me. Okay, so this answer was provided by Jack M, and so everything is owed to Jack for this response. But take a look at this little video, right? So what you can see is that they're going over multiple points in this domain, A and B, of your function. And what the red line is plotting is the slope of the secant. So you can see it's sort of varying continuously. And at the very end points, it's equal to f prime of A and f prime of B, right? So it starts at f prime of A, finishes at f prime of B. And essentially what you can see is that that secant line is going to take on every value of slopes between f prime of A and f prime of B. That's what this little illustration is giving you. And as you can see from the little explanation underneath, since the secant line takes on all of those values, well then, boom, we apply the mean value theorem, and it tells us that so does the derivative of f. So this is the geometric interpretation of this, and it's telling you that you use first the secants. Once you have the secants, then the mean value theorem tells you that your derivative takes on every value in here. Now, let's take a look at the proof of this. And the proof is not too bad. So let's start with it. There's a few things that we can knock off really easily. And really all the proof is dealing with edge cases. So let's suppose that A is less than B. And I'm going to make the assumption that f prime of A is less than y, which is less than f prime of B. Now, there is nothing that says that f prime has to be smaller than f prime of A has to be smaller than f prime of B. I could have the other case where I switch these two things around, and f prime of B would be less than f prime of A. But if that's the case, you can just set G is equal to minus f, and then you get yourself all the way back to this case. So this is like, this is standard in mathematics. What you basically do is you figure out that only one case matters, right? We've done this over and over. And so I'm only going to prove the result for the case where f prime of A is smaller than f prime of B. But I just want you to know that you can do both cases and that one basically follows from the other. Okay, here's what I want to do. I want to define, let's call it phi of x, and this is f of x minus y times x. Okay, so first of all, notice that, so we have phi is definitely a continuous function on the interval AB. And that comes to the fact that y is fixed, right? So don't get confused. There's no derivatives with respect to y. It's a fixed value that we've chosen between f prime of A and f prime of B in order to show that the mean, or this intermediate value theorem, actually applies here. Okay, so then when you take a derivative of this thing, so we want to show that there exists some x bar between A and B such that phi prime of x bar is equal to 0. And why is it that I want to show that phi prime of x bar is equal to 0? Well, if I calculate the derivative of phi prime, that's f prime minus y. And so if that's equal to 0, that gives me f prime is equal to y, which is, as you can see here, exactly what we wanted to show. So essentially, this comes down to showing that there's a critical point of this derivative, or of this function phi. Okay, so first of all, by the extreme value theorem, I'll write this one out. Sorry, extreme value theorem. Phi must have, well, it must have both a max and a min on the interval AB, right? That comes from the fact that you have a closed interval and you have a continuous function on it. Now, we have shown already that if such an extreme point, so such an extreme point, either a max or a min, is an interior point, so i.e. in the open interval AB, then we actually proved that phi prime is 0 at this point. Sorry. And we are done. Right? So what this says is that, by the extreme value theorem, there is a maximum and minimum value attained by phi on this closed interval. Now, if that either the maximum or the minimum is attained at an interior point, so not at the endpoints of this interval, then we've already proven that the derivative vanishes at that point. Boom, we're done. So then we're only left to guess or to interrogate the case where you get extreme points at the endpoints. So we will suppose the extreme points, well, we'll suppose these things occur only at the endpoints. A and B. And to find a contradiction. Okay, so in fact, we're going to have 3 cases. The first 2 cases are handled identically, so I'm really just going to prove the first one. And then the third case, we'll see that this actually just gives you a constant function, and so you're just done. Nothing exciting happens. So let me start by the first case. So we have 3 cases. Let's put that on this board, and then let's go to a new board to start with the cases here. Okay, so case 1, let's suppose phi of A is a max and phi of B is a min. Okay, so in this case, then what do we have? Well, we're going to find that there's a massive contradiction here. If I take the derivative at A, this is the limit as h goes to 0, of course, from the right, because this is a closed interval, so I can only approach from one side. But this is phi of A plus h minus phi of A divided by h. Now, because phi of A is assumed to be a maximum, that means that phi of A plus h is less than or equal to phi of A, which means that for every value of h that's not 0, this quotient is less than or equal to 0. And so, of course, that passes to the limit. So that tells us that the derivative at A has to be less than or equal to 0. And this tells us that f prime of A is less than or equal to y. Okay. That's okay. now, what else happens? Well, we can do something similar. We can say phi prime of b. This is, again, the limit as h goes to 0, this time from the left. Again, closed interval, approaching it up from the one side that we can approach from. Phi of b plus h minus phi of b divided by h. Now, in this case, you have a minimum, which means the top of this, this quotient is greater than or equal to 0 because phi of b plus h is greater than or equal to phi of b. But h is approaching from negative values. So you have positive on top, negative on the bottom. Again, you've got less than or equal to 0 here. And from exactly the same arguments as above, this also gives that f prime of b is less than or equal to y as well. Now, this is impossible, right? We already assumed that y is between f prime of a and f prime of b. So this contradicts the hypothesis. The hypothesis. So no good. Let's put a big X there, right? This case doesn't work. Okay, what's the next case? Well, the next case is if you reverse these things. So you say, suppose phi of A is a min and phi of B is a max. Then just proceed as in the same case. So same arguments as in case 1 lead to a contradiction. All right, that one's out too. No good. Final case. Well, the final case is, so finally, let me write it out as I say it. If one endpoint is both a max and a min, right? So the derivative is sort of equal to 0 here. Then phi is a constant function. And this gives me that phi prime of x is just 0 everywhere. So why is this the case? Well, your extreme value theorem tells you that you have maxima and minima in this case. So if it is the case that your endpoint is both a maximum and a minimum, well, then the extreme value theorem says that there's nothing that happens in between, right? The only value that you can attain on this thing is that max and min value. And so therefore, your function has to be completely constant over the entire interval. And we proved using the mean value theorem in the last lecture that if your function is constant, then your derivative is equal to 0. Actually, we didn't use the mean value theorem for that, right? You can just do that directly. That tells you that your derivative is equal to 0, which is what we wanted to show. So this covers all of the cases. So essentially what we've done with this proof is we said, okay, well, if phi has a max or a min inside the interval, we know the derivative has to be 0 there. We've already proved that. So check. That's one case out. That's one case done. Then we said, okay, imagine your maximum and minimum occur at the endpoints, A and B. Then let's ask ourselves, what are the possibilities? We have 3 cases. We saw the first 2 are impossible. And the third case tells us that my function has to just be constant, which trivially satisfies what I was looking for. Remember, the whole purpose of how we were going through this proof was to show that phi prime is equal to 0 at some point. In the case when your function is constant, it's equal to 0 everywhere. And so it's trivially true. All right, we did it, right? We got to state and prove both versions of the fundamental theorem of calculus. And again, what I want to emphasize is what this theorem does is it relates integrals and derivatives together. Now, I really want you to take a look at the difference between version 1 and version 2 and see sort of how that relationship is being done. In one case, it's using integrals to understand derivatives. In another case, it's using derivatives to understand integrals. And the last piece that I'll reiterate is try and prove that mean value theorem for integrals yourself. Remember, you should just interpret it more as an intermediate value theorem than really a mean value theorem.